This is CPE 133. This is the Introduction to Verilog. This is Chapter 3 from the Free Range Verilog Foundation Modeling text. So what we're going to do in this video is describe the approach that the Free Range Verilog Foundation Modeling text is going to take to learning Verilog. We're also going to describe some of the basic features of HDLs in general. And lastly, we're going to describe some of what I call the invariant issues of Verilog, which is essentially stuff in Verilog that you don't need to know anything about Verilog to know and always use, and you'll see it's not a big deal later. So the approach that the Free Range Verilog Foundation Modeling takes is to get you up and going real fast, generating or modeling circuits. And the issue is there's a lot of stuff in Verilog. We're not going to even attempt to tell you it all. Something I'm going to do is try to tell you the stuff you need to know to get up and running up and modeling some circuits. So we'll start with basic circuits, and that being the case, we don't really need to know super in-depth Verilog modeling details. So you get more details as you go along, and typically you're not going to get a super ton of details in this course, but you're going to be generating some cool circuits. Hopefully after this course you continue with Verilog. And the big issue here is you're not going to learn modeling circuits by reading a book or listening to a video. You're only going to learn it by actually sitting down and doing some modeling. And so I encourage you to sit down and do some modeling. So there's lots of Verilog resources out there, including books and just tutorials on the web. I absolutely encourage you to go hunt those down and use those to help you in any way you can. So digital design, HDL modeling, there's two types of digital circuits out there. It's broken into combinatorial circuits and sequential circuits. Sequential circuits have memory, their ability to memorize details, or memorize bits, we'll say, and combinatorial circuits which have no memory. So essentially, a combinatorial circuit, the outputs are a function of the inputs. With the sequential circuits, the outputs are a function of the sequence of inputs. So that's where the sequential comes from. In hardware description languages, there's essentially two ways to model circuits. Essentially, it's at a high level or a low level. So low level, what we refer to as data flow modeling, and essentially it's kind of using gates to control your circuit. And so it's really a direct approach as opposed to behavior modeling, which is a high level approach. And what you're doing is essentially you're describing how your circuit should work, and then you're sending it off to another piece of software to actually do kind of the low-level modeling for you. So it's behavioral modeling, very powerful because a lot of the grunt work, dirty work is done by the tools itself rather than you doing it in something like a data flow model. So big issue out there, you're designing a circuit, should it be sequential or combinatorial? Should I use behavioral or data flow modeling? And so these are just things that there's no set of rules that are absolute to answer all these questions. There are some sets of rules that we're going to follow that can be really helpful, but typically the answers to these questions are contextual. And so the point of this slide being is you need to understand just the basic digital design concepts and the basic HDL modeling concepts, particularly Verilog modeling Verilog modeling concepts, because that's what we're going to be using in this course. If you try to start modeling without understanding digital design or just the basics of Verilog modeling, you're going to regret it. Your circuit's not going to work. You're going to hate life because your circuit's not going to work. So anyway, to be effective, you need a basic understanding of both HDL and digital circuits in general. So these are the Verilog invariants here, and the stuff I think it's easy to follow when you're first starting out, but just keep in mind that these things exist. So we'll go through this fairly quickly. It's not a big deal. So what you have out there is we'll call them identifiers. Essentially, they're just names to describe things in Verilog, such as the module names and the signal names. Essentially, they all need to be alpha values. You can use numerical values in them, but you can't start the identifier with a numerical value. Also, you can use underscores, quite effective and kind of self-commenting. So ideally, your identifier should be self-commenting, which should it's just an approach to use the label to indicate kind of the purpose of that module or that signal. So here's an example here. This shift result could be the output of a shift register, which is a better name, more descriptive name than just simply val. Anyway, self-commenting, use it. Verilog is case sensitive. Primarily this has to do with identifiers. For example, this shift val and these two shift val here are actually different identifiers simply because it's case sensitive, and the S in one of these identifiers is capitalized and the other one's lowercase. So these are two different identifiers. So Verilog is case sensitive. Additionally, the white space in Verilog is ignored, including tabs. Tabs is going to be a white space, but keep in mind when you're coding your Verilog text here, you never touch the tab key. You touch the tab key, and it's going to make your code look ugly when you print it out. Additionally, blank lines, another piece of white space. Use those liberally to separate ideas and make your code more readable. There's two types of comments in Verilog that follow essentially C++. You have the double slash comments, so everything after the double slash is ignored. And then you also have the slash star comments, so everything between the slash star and the star slash is ignored. So the double slashes are a single line comment. The slash star is kind of a multi-line comment. It's parentheses in Verilog, so it's not required in many places, but if you don't use parentheses, that means your models are required, or you're required to rely on precedence rules. And quite frankly, I don't know what the precedence rules are, because I don't need to know them, because I use parentheses liberally. Additionally, use parentheses. That makes your models and your code in general more readable. So there's a bunch of reserved words or keywords in Verilog. This is a partial list here. These are the variables that you might use. The ones not in this list are things you may not use here. So in general, all the Verilog statements are terminated with a semicolon. Initially, it's a challenge to know what exactly a statement is in Verilog and what's not a statement. So just keep in mind, statements are terminated with a semicolon, very much like C programming. So in summary, this is CP 133. We're going to use Verilog to model our digital circuits. We're going to start off very simple. We're not going to tell you everything about Verilog to start off with. We're going to kind of build up to it. So at first, you're just going to get a small subset of details, and we'll add to that later. So digital circuits design and modeling generally, in general it's about sequential and combinatorial circuits, and as far as HDL modeling goes, it's an issue of which type of modeling you're going to use. So data flow, which is understood to be low level, or behavioral, which is understood to be high level. A bunch of invariants in Verilog. The language is quite flexible, but there's a couple things you need to follow, such as these invariants. And in the end, the whole idea is to make your models is as simple and as readable as possible for other humans. The synthesizer, the software isn't going to care that much, but you are going to debug your code, you're going to share your code with other humans. You want to make it as readable as possible.